Ranvical RG. So, here it turns out that if you make a change of variable grad h is minus grad h is u. If you do this change of variable grad h is u, then this is a minus sign, minus grad h is u. Okay. So, then it turns out that we can get a new equation for u, and the equation for u is this. Okay. So, you just take a gradient of this equation. Okay. So, in fact, you can obviously see this one and this one here, and if I take a gradient of this, so gradient h is already u. So, this is u dot, it turns out it is u dot grad u. Okay. So, this is Burger's equation. Okay. It's like Navier-Stokes equation with pressure being 0. Okay. Now, we showed in previous lectures that Navier-Stokes equation respects Galilean invariance. That means the equation remains unchanged if I go from one initial frame to the another initial frame, and the transformation is you add a velocity, right, u naught when I go from one frame to other frame, and that invariance leads to condition that lambda must not change under scaling. Okay, this I showed in the class. So, the same argument works here, and that proves that lambda remains unchanged under RG. So, this is unchanged. Okay. So, our idea would be to renormalize nu and d. Okay. D is the coefficient. So, eta x t, eta x prime t prime is 2d delta x minus x prime delta t minus t prime. Okay. So, d is the prefactor, strength of the noise. Eta squared is essentially 2d. Okay. So, that d is renormalized. So, let us see how to do it. Now, please note that this is non-equilibrium system, right, because there is a time dependence. So, this system has frequency, there is a time. Okay. So, this is not same as Wilson RG, which had no time. Okay. So, that is the difference. So, we are going to do RG for a non-equilibrium system, or which is system is has time dependence. Okay. Well, if you look at in some detail, for white noise eta, KPZ can be argued to be in equilibrium. Okay. But I think I will ignore that part, that is the subtle part, but well, basically it is time dependent equation, I am going to do RG. Okay. So, frequency is a parameter here. Okay. So, this is my equation. So, we can write down, we can do the similar thing as what we did for Navier-Stokes equation. Okay. So, I want to convert this to Fourier space. Okay. So, let us convert it to Fourier space. So, I am going to write it here dh by dt h of k, right. So, h of x will become h of k, in fact h of kt, we will use h of kt. Well, no, I think I am going to use k omega. In fact, the idea is to use k omega. That I am following standard procedure. Okay. I am going to make some deviation from what I did for Navier-Stokes. Navier-Stokes I did with T and K, but KPZ paper, that Kardar Parasi Zhang paper, they use frequency and K. So, d by dt will give you minus I omega, correct. I mean, we write h of x t as integral dk d omega, in fact by 2 pi to the power d plus 1, d for k and 1 for omega, then h k omega e to the power I k dot x minus omega t. Okay. That is my transformation. So, I just substitute here and take the derivatives. So, I will get minus I omega here, h of k omega, and this you take it to the left side. So, new Laplacian will give you what? So, here minus nu k squared, right. When I take it to the left hand side, I get plus nu k squared u k omega. Okay. Noise will be just straightforward, nu x t becomes eta x t becomes eta k omega, right. But with this nonlinear term will be convolution, it is a product, so it becomes convolution. So, that is going to be lambda by 2 grad h. So, this you can call it grad h multiplied by grad h dot in fact. Okay. So, now I am going to replace h by e to the power I p dot x minus omega p dot omega pt. So, here the argument will be I should replace this by p in fact, and this omega by omega p. Frequency, there are 3 frequencies, one for k, and well there are 3 independent frequencies, but I am going to write this for one for k is like paired, k is paired with omega, but p I am going to pair with omega p, and q I will pair with omega q. Okay. So, grad will give you I p, right. So, gradient gives I p, no, h of p omega p, and the other guy will give you, when I take a gradient, when that h is function of q and omega q, I q h q omega q. Okay. So, these are vectors I p and I q. So, that gives you I times I will give minus 1 minus p dot q, this is integral h p omega p h q omega q, and I need to do this integral, right, dp by 2 pi to the power d omega p by 2 pi. And what is the condition on this kpq? Conservation of linear momentum, that gives us the condition k equal to p plus q, exactly like Navier-Stokes, and omega equal to omega p plus omega q. Okay. So, this is a condition. Now, this is a nonlinear equation, it has become even worse, it has become a convolution. Okay. So, what do I do with that? Okay. So, the idea is to do it perturbatively. Okay. The way we did it for Navier-Stokes, very similar scheme. So, this 2h I am going to write as these 2 lines, HP here and HQ. So, in fact, is P 4 vector, I will put 4 vector. 4 vector, P 4 vector means P vector omega P, okay, and Q also 4 vector HQ, and what is the coefficient in front is PQ, P dot Q minus sign, right. So, this is my Feynman diagram. Okay. If I assume H and these 2 H guys H omega H p hat and H q hat to be random, well, what kind of random we will assume kind of Gaussian. Then if I average them out H p H q, well, then I will get 0. Okay. But before that I need to do some, since I am doing RG, then I need to separate the scales, right. We did that before, no. So, RG, what is the RG procedure? We divide this wave number space into various shells, in fact log bin shells. In log scale they are linear, but in real space it is power law. So, this is kn plus 1, this kn and this kn plus 1, okay. They are supposed to be equal, okay, and this kn minus 1, and kn we write as b to the power n, right. This is what we did it for Wilson RG. So, I am following Wilson RG procedure. Now, I am going to rewrite this equation for less variable and greater variable. So, this is greater variable blue one and less variable, and I am going to coarse grain for wave numbers in this band. This idea is clear, no? We did it coarse graining. Coarse graining means high frequency modes or high wave number modes, which are small scale modes, I am going to average out those modes. So, the equation, new equation which I am going to write as, okay. So, since my, so let's write in the next page, okay. So, let's write in the next page. Okay, I think we will write in the next page, okay. So, let's okay, this is also filled up. Yeah, so that is what I am writing it here. Okay. So, here I made this k space, and we have like that. I am going to extend it here. So, kn to kn plus 1, okay, and this part I am going to average. So, we rewrite this equation for h as h less, is h less, we will have h less, then h less, h greater, then h greater, h greater, right. Of course, we will have h less of p, h greater of p, h less of q, right. So, there are 4 possibilities. So, I have this k equal to p plus q, okay, p plus q, but p can be small and q can be large, or p can be large, q can be small, or both are large. So, depends where is p in q. By the way, please keep in mind that k can be here, p can be very large and q can be like that. In fact, this corresponds to greater greater. K can be tiny, but p and q can be large. So, there all these possibilities exist. The idea is how much they contribute, and that comes from calculation. Okay. So, this is the integral. Now, we have this integral, this one dp omega p. By the way, I do not write dp dq. If I write dp dq, then I need to put a delta function. So, we vary only p because q is not an independent variable, q is k minus p. So, I normally prefer this, I do not write dq, otherwise I need to put a delta function. Okay. So, we have dp d omega p divided by 2 pi to the power d plus 1. Okay. So, this integral. So, the circle equation inside the red circle or inside the red oval, actually not circle, that is same as original equation, right. But these are new, these three are new terms, and they will lead to some correction to nu, the way it happened for Navier-Stokes or it happened for Wilson theory. So, the parameter r, which is connected to the temperature, which was changed because of this greater term. Okay. Now, if I assume that greater is a random variable, but less is not a random variable, then these two averages will be 0, right. So, this will become less is not averaged, but greater is averaged. But so, for example, look at this term, we write this as less is not averaged, to h cube, this comes out, and h greater p, and h greater p is 0 because h is a random variable with 0 mean. But what about greater? So, greater is a tricky part, and let us write this one in the next slide. So, I am going to write, so right hand side RHS, which will give us non-zero value, is integral dp d omega p by 2 pi to the power d plus 1. This is annoying to carry it out, but h less than p, h greater than p, sorry, h greater than p, h greater than q, 4 vectors, okay. And there is a p dot q with a minus sign. So, we write this as this 2h, h of p, h of q, and in front is minus p dot q, and of course, we need to integrate. Now, to 0th order, this is 0, right, because if I do the average, p is not equal to k, so that will give you 0. So, 0th order is 0, but I want a non-zero contribution. So, I go to the next order. So, to get a next order, what should I do? I am going to expand by Green's function. HP I am going to expand as the Green's function, okay. So, if you recall, HP will be what? HP, there is a Green's function inverse, G not inverse, bare Green's function, that is function of original viscosity, it is original nu. So, this was, remember, is what, minus I omega p plus p nu p squared HP. So, we write this as Green's function inverse. The right hand side will be again the nonlinear term and noise. So, look at the nonlinear term, it will be lambda integral. So, now I should use a different variable r and s, right. So, let us use a different variable r and s, right inside, minus lambda, well minus or plus, so this plus lambda, then r dot s with a minus sign. R and S are two variables, two way numbers, and we have P equal to R plus S, right. That is what convolution means. And inside will be H of R, R4 vector, H of S4 vector, and now I have dr R4 vector divided by 2 pi to the power T plus 1. R4 vector means I have corresponding frequency as well. Okay, dr vector d omega r. Okay, so this is what is the Green's function. So we write is the Green's function like that, and the Green's function will have 2 h. So one h will go like that and one h will go there. Okay, now this technology is very similar to what we did before. So this is h of q 4 vector. So this must be h of minus q, right, to give a non-zero value. But look, so now we can, in fact we can figure out what should be this guy. So if r is going in, so r is minus q, okay, minus q vector, then what should be s? You can easily guess what should be s, not guess, you can derive plus s. So from here I say that s equal to p plus q, and what is p plus q? Is k. So this h of k less, okay. Okay, now this guy is minus r dot s. Well, r dot s is nothing but q dot k, because r is q and s is p, s is k. So q dot k. So all that follows from this conservation stuff. So which will correct the viscosity? The loop diagram. So correction will come from this loop diagram, which is Green's function and correlation function. Okay. In fact, there will be minus sign because I need to take it to the left hand side. So delta nu of k, okay, which is, there are integral d of p4 vector. I am not writing 2 pi by d plus 1, okay. Then we have p dot q, minus becomes, well, forget about the sign, I mean the detailed stuff we need to do it yourself, q dot k. Well, I mean forget means do not focus on it, you need to of course keep it in detailed calculation, but let us focus on the idea. And it will be g of p 4 vector, right, g of 4 vector, whether g of 4 vector is what? G naught, that they use Kardar Parisi Zhang, they are not using self consistent procedure, they are using the original G naught. So G naught of p will be what? 1 divided by, so this is inverse, right, so 1 minus omega p plus nu p squared. Okay. Now we have correlation function C of q, well they are omega p as well, okay. Now C of, what is C of q? So we can expand this one. How do I compute C of q, which is h q and h of minus q? So it is written like this. So here instead of p you replace by q, okay. So this G naught inverse will go to the right. So just focus on this is h of q, h of minus q. So I am going to write h of q, okay, is G naught of q, right. So this guy will go to the right, and the nonlinear and the noise term. Do not put the nonlinear term now because that will go to higher order. Put the noise eta q 4 vector. Okay, now G naught of minus q, eta of minus q. Okay, so eta will give you what? Eta q and eta minus q will give you d, right? That strength of the noise. So if I do all this stuff, I will get from this eta and this eta, I will get strength of noise d, integral dp, and there are this p is also there, p dot q, q dot k, and the 3 Green's function, G naught of p, G naught of q, G naught of minus q. Okay. So this is the term I am going to get. Okay. Now we make the assumption that this G naught has low frequency. Okay. So, that will give us low frequency means this omega will go away. That is the assumption made in this calculation. So, it essentially gives a nu k squared, nu p squared, right from here. So, the 3 G. So, the one will get 1 by nu, 1 by nu, 1 by nu. So, outside will get d by nu cube and integral dp, and this integral is not done for all wave numbers. So, where should the integral be? Is the shell, right. In Wilson we did for lambda by b to lambda. So, this integral is done from kn to kn plus 1, which is kn to kn plus 1. So, which is width of b, this is this ratio is b. Okay. So, that is the integral which is done, and okay, some numbers will come. Okay. Is the idea clear? And that is going to correct the viscosity. So, that is the next slide. So, we have this 3 Green's function I wrote, right, and this is the 2 etas and all that. So, I already, so by the 2 lambdas, one in the left, one in the right. So, there is lambda squared d, and the 3 Green's function gives you nu cube, under the assumption the frequency is small. Okay. So, this is by our nu less, nu correction, this is the correction, this guy, lambda square d by nu cube, and because I am doing volume integral of this sphere, then the kd is a surface area of the sphere, right, surface area multiplied by thickness, and this part is the thickness part. Okay. Now, that detail I will leave out, that is a new, but this is coarse graining right now. But if you recall Wilson procedure, we also need to do rescaling, right, remember there is a rescaling. So, after coarse graining the system has become, this is the thing so we have this big system which had many squares, in fact they are 16 squares, but after coarse graining it becomes 4 squares. So, my squares become big. So, I need to rescale it to make it like small earlier square, and that scaling is like b to the power something, and we know for nu it is b to the power z minus 2. That factor which we derived earlier, in fact exactly same factor b to the z minus 2. If you recall, the new Laplacian h had the b to the z minus 2, right, then that is z is equal to 2, and that is a disaster, right. I wrote that. So, there is a prefactor for b which is b to the z minus 2, and we make this thing that b is equal to e to the power l. We did it for earlier, no, I mean for Wilson theory as well as for mass renormalization. Okay. So, if I substitute it, then this looks pretty nice, that b is expanded as exponential b to the power z minus 2, in fact I have done it here, e to the power z minus 2 times delta L, and that is expanded for small delta L is this. Now, you substitute this nu less as nu times this stuff. So, these guys will also give correction. Okay. So, overall I get, in fact I need to substitute it here. So, this guy is 1 minus, in fact this is called g squared. Okay. This is called g squared kd, and integral, this integral. Okay. This integral is basically 2 minus d by 4d, this part, and this part is by the way there will dl will come here, this integral, no. So, there is a thickness, and thickness is dl, and there is a delta L here. Okay. And I think this part is plus, this part is plus by some calculation, there is a stuff, and this part is 1 plus delta L z minus 2. So, to leading order in leading order for delta L, I will get z minus 2 from here, and this part will come here, the kd g squared 2 minus d by 4d. So, and there is a nu in front. Okay. This nu is here. Okay. So, d nu by dl is nu z minus 2 plus kd g square, is that. Okay. So, nu is, in fact if this was not there, then it would be z minus 2, but this is a correction by nonlinear interaction. Okay. This for nu, got it. Now, so this is the Wilson flow equation, right. Remember we got to fixed point and do Wilson flow equation, that is what we got.